I will tell you when to change it.
Sure.
Okay, because
Sure.
I follow my screen also.
Sure.
Okay, the live stream is on, and I also started the recording, and then I'll head out. Okay.
Sure.
Did you check the live stream?
Okay.
Thank you.
See you. Bye bye.
Let's wait 5 more minutes and then we will start.
Good.
Since Antonius is there, can I ask you if you can see the slides, Antonius?
Can you hear you? They should be able to hear you. Maybe he has
So
to
you can,
unmute.
they can see. Okay.
Okay. You want to introduce me in the meanwhile?
Sure. Hi everyone. Today we are having Professor Ivo Desmedt, who is distinguished professor at the University of Texas at Dallas, honorary professor at UCL, and fellow of the International Association of Cryptologic Research, IACR, and member of Belgium Royal Academy of Science. He received his PhD from the University of Leuven, Belgium. He holds position at Université de Montréal and Floridian State University. Most of you already know him because of his many famous works, especially in e-voting and threshold cryptography. Today, Ivo is going to talk about one of his recent work in secret sharing.
Thank you for the introduction. Okay, so today I will be talking about framing and realistic the secret sharing. And so what I will start with, so what I will start with is what is secret sharing, because I presume not all of you actually are familiar with what secret sharing is. And then I also briefly will talk about why is it important. And then I will talk about rational secret sharing. And it has been a little bit controversial. And so we try to solve that controversy. And I will talk about an approach that we use to avoid the controversy. And so after that comes the, maybe you can move this a little bit this way. Okay, better, good. So afterwards comes the second part of the talk, which is on framing in the secret sharing schemes. So we will start with a simple comment on Shamir Secret Sharing scheme, which I will explain. And then we will actually give you some examples of how framing works and what it actually is. And then we will conclude and also give some open problems. So I want to thank the Johnson Endowment for making this research possible. So what is secret sharing? It actually goes back to work that was done in the 1960s. It may even be older, where you have a number of scientists who want to open a mechanical safe, and you want to make sure that none alone is able to open this mechanical safe. And so you have a number of scientists, and for example, you want to make sure there are at least 2 of them that are present in order to open that safe. So that used combinatorics, and then Blackley and independently Shamir proposed it in the context of backup of data. And there's a big difference with keys and data, because with data you can compute, and with keys, mechanical keys, you cannot. And so therefore, that made the solution much more efficient. And so a secret sharing scheme is going to have 2 algorithms. One that's going to create the shares starting from a secret, and I write here K, later we'll use S0 for representing the secret. And then that's going to produce shares. And then there will be a second algorithm that will allow authorized parties to basically regenerate the secret from their shares. And so you see there this Greek symbol that basically says that's an access structure. Yes, you can use the mouse. Okay, so with the mouse, I can show you the symbol. So this is the access structure here. And then this B is a subset of the participants that belongs to the access structure. So if you are a subset of the participants that belongs to the access structure, you can recover the secret. And if you are not in there, then you cannot. Okay. And so you're going to have a dealer going to generate the secret shares starting from the secret. And you're going to also have a public directory, X1, Xn corresponding to the N participants. X1 corresponds to P1, etc. So you also have it if you are not authorized, then you should not be able to recover the secret. That's the first required property. And the second one is that if you are authorized, then when you do the computation, you find back the original secret, which in this is written as the K. So schemes that satisfy the following property, that if you are not authorized and you combine all your shares, that then you have no clue about the secret. If that's the case, so that's called, from a probability viewpoint, it's called independent. If you have this independence property, then the secret sharing scheme is called perfect. And I mentioned 2 secret sharing schemes, the one of Blakely and the one of Shamir. The one of Blakely is not perfect, the one of Shamir is. Now, note that access structure is very, very different from access control, because access control in computer security, you give access to individuals. Okay? In access structure, you're going to give access to subsets of parties. Okay? And we're going to come back and give some examples of that later. And the most known scheme is Shamir threshold scheme, which I will basically talk about later. So, what happens is that today, I checked that yesterday or the day before, but yeah, this week, when you look at Google Scholar and you type in Shamir's paper, then you will find that that paper has 17,000, more than 17,000 citations. So it's one of the most cited papers that Shamir has. And so you will wonder, what the heck is there still to do? Because if you have 70,000 papers, kind of everything has exhausted what should be exhausted. So why is secret sharing important? So from an academic viewpoint, it has lots of citations, but there are also other reasons. So it's unfortunately rarely used in practice, although you could say you see IBM at the bottom. So there might be some rare applications where IBM uses that. But it's the foundation of a lot of theoretical schemes and protocols that are potentially practical, such as threshold crypto. And so in that context, I heard that I think Visa and or MasterCard are using threshold crypto. Unfortunately, they are using an impractical scheme, which has been advertised as practical. And so their implementation is not so very practical. So it's also used in secure multi-party computation when you use the unconditional setting. It's used in private and secure message transmission, and also in IBM's multi-cloud, which I presume is used in practice. So I'm now going to talk about rational secret sharing. So Halpern and Teague, they actually introduced what they call rational secret sharing. And so what they did, so the parties have to reconstruct the secret. We talked about that. It's one of the algorithms that has to be there. And they regard the reconstruction process as a game. Okay. And what they were able to show is that one of the parties may actually refuse to reveal their share, so the reconstruction may fail. Okay. Moreover, a refusal to reveal the share may be a dominant strategy of a party. And the impact, for example, would be that in secure multi-party computation, parties may refuse to execute the last step, and so therefore the function will never be computed. Okay. So obviously this was controversial when this came out in the crypto community, because people said, yeah, is this realistic, etc. And we'll talk about that in a minute. So in particular, my co-author Slinko objected against the aforementioned conclusion and claimed that it was sometimes unrealistic. And so his major claim that he made to me and to other people too is that he claimed that the conclusion of rational secret sharing only applies in a situation where all parties are adversarial. And so his favorite example was that the secret corresponds to a map of a treasure. Okay. And so there are interesting cases of treasures that are buried. There is a treasure buried somewhere by the French army that buried a lot of gold. And then what actually happened is that nobody knows where this gold is anymore. It's apparently lots and lots of money. But so imagine that they would have made a map of it and then cut it in pieces and given everybody a share. And now they want to reconstruct that. Unfortunately, one person, since this happened centuries ago, one person lives in France, the other person lives in Britain, etc. And so why would they send to each other the shares? Because the one that lives in the United States, at the moment that that person actually gets the shares from the other, that party can rush to the location, dig up all the gold and get all the money. Clear? So therefore, the other party is saying, no, we're definitely not going to share our share. And so therefore, the secret will never be reconstructed. And so what happened is that then to counter this argument, we looked at potential applications of secret sharing, and now we consider a few scenarios. So one scenario is authorizing a project. So the secret gives access to a bank account from a city. And the parties are actually the city council. And so the common good is being able to use the funds to build a new tube line, let's say the Elizabeth line. Okay. Now, so that's a common good. So what is a common good? It's actually something that was introduced by Aristotle, who is considered the parent of common good. It's something that everybody benefits from. Clear? So it's kind of the opposite of this treasure, where only the person who will be able to dig it up the fastest will be able to benefit, the others don't get a benefit. Clear? So that's a major difference here. So another example is launching a nuclear missile. So in the former USSR, any two of three top state officials needed to activate their nuclear suitcases to launch a missile. You could say there's no common good because it's only going to be common evil. But from the USSR viewpoint, the common good was defeating an enemy, a common enemy, and so therefore, from their viewpoint, in case it was needed, that would have been a common good. So in terrestrial crypto, you can make many examples. One example is signing a message. And one of the original applications was that the message would be signed on behalf of an organization, such as the city council. And so therefore, since the city is basically making the declarations and statements, they have to be signed. And so people there, their job is to actually then sign these messages. And so therefore, the common good is this signed message. Now, evidently, if it's something people don't want to sign, if you think about a democracy, you have very often proposals that are made for new laws where people say, no, we don't want that law. Then they're not going to co-sign. So, but that's again in the interest of the organization not to co-sign. Okay. And also note that in the case of threshold cryptography and MPC, secrets should not be recovered. Only the final result should be recovered. And so again, it's not because you're not doing something that therefore it's bad in this context. So now the question is, how were we modeling realistic secret sharing? So the second, the ones in which you have a common good instead of having all the parties compete with each other and be adversarial, that one, the second one in which basically you have a common good, that one we call realistic secret sharing. And so to model that, we assign to each party pi a value and I when the common good is achieved. So a party pi will receive something, it doesn't need to be money, it could be time. If you have the Elizabeth line now in London, once it will be working properly, people will be able to save a lot of time. There are already people who are saving a lot of time, but not as many as was originally planned. That's going to come. That's the common good. So if you think about people being in the city council, then that helped their area where basically otherwise they wouldn't have this line. And so then you're going to assign to each party that participates in an attempt to recover some cost C to participate. Okay. So obviously, if the secret is not recovered, the party will only have a cost, while otherwise it's going to gain a difference between the two. So obviously, if the cost to participate is higher than the common good, the best strategy is not to participate and nothing will happen. However, when the cost to participate is less than the common good that that party will obtain, then we were able to prove that for the minimal authorized coalition of the access structure, participation is a winning strategy. And I don't have the time to give the proof. So later on, I will give you the references and then you find the proof in reference number 3. So Shamir Secret Sharing Scheme. So now I'm going to talk about the second part of the presentations. So Shamir Secret Sharing Scheme is basically a polynomial, which we all learned in, I presume, high school. The only difference is you're going to use a finite field, but that doesn't really make a big difference from what we want to explain. Okay. So you have a polynomial and the value at location 0 at x equal to 0, that's the secret. And the rest of the polynomial is chosen randomly. So if you run the polynomial, except that the a is 0, that's the secret. And that's how that the secret was distributed. So what are the shares? So if you are participant pi, as I mentioned in the second or third slide, to participant pi correspond xi, that's in the public database. And so the si, the share of I, will be nothing else than f evaluated at xi. Okay. And now what we used to teach in computer science was numerical analysis. Now, some people have objected to say, wait. We still, at some universities, numerical analysis is still being taught, but it's no longer a required course. Okay. So when I was a student, all engineers had to learn about Lagrange interpolation. And so Lagrange interpolation, when you have basically, you know, a function at certain values, the image at certain values, then you can actually construct a function, a polynomial that will going to go exactly to these points. And that's done with Lagrange interpolation. And once you have Lagrange interpolation, you can then find the whole polynomial, which will allow you to find f0. And so then you actually found the secret. Now, in order to do that, you need, if the polynomial is of degree at most t minus 1, so if these values were chosen randomly, at minus 1, at minus 2, etc., up to a1, then you need at least t parties in order to be sure that you have recovered a0. Okay. So now I'm going to start with trivial comments on Shamir Secret Sharing scheme. And trivial comment is any T parties cannot only recompute the secret key, but they can find the shares of all the participants, assuming Xi is public. Yes, why? Because if you look at Lagrange interpolation, what does Lagrange interpolation does? It recovers you the full f of x. And so then you can do the same. Once you have the full f of x, you can do the same as the distributor. And you can basically find everybody's L share. Now, why is that so important? Okay, so let's take the impact of that. Suppose that T parties use their shares to recompute the secret before they're allowed to do that. So suppose somebody made a legal will and then says, when I die, you can start from your shares, and then you can actually compute the legal will and then know who gets what. But some people are very curious, and so they want to do that before the person dies. Clear? So you may have T parties who saying, hey, they're so much tempted to try to do that, they're going to do it earlier. So if you now are working in a financial institute and you want to do a non-authorized transaction, okay, a fraudulent transaction, then it may also be very tempting, because you have to know how many billions of dollars are actually transferred today using crypto. It's enormous. Everybody talks about Bitcoin and blockchain, but everybody forgets that since the 80s, this is used, cryptography is being used to transfer funds. Also, if you look at your credit cards, etc., there's a chip inside, and there's also crypto in there. But that's small amount of money. So I was talking about bigger transactions, where you need 2 people or more before the transaction can take place. And so you may have corrupt people who is going to try to have this done for a non-authorized transaction. Or you may have, in case of threshold decryption, you may have people who need to decrypt it. They will decrypt it, and they will keep the plain text for themselves instead of sharing it with the other n-T parties, which is not allowed. And if you think about secure multi-party computation, a lot of you know what it is. So what you're going to, so in secure multi-party computation, what you're going to do is you want to compute a function of x1, x2, x3, etc., where x1 is a secret of party 1, x2 is a secret of party 2, etc., without revealing the xi's. And how does it work in the unconditional world? All these xi's are going to be shared. And then people compute with that, and then the final result, that one, are all shares, they're shares of the final result. The share of the final result, that will be computed doing a recovering algorithm, and then you will find the final result. But since every participant shared is the xi's, it may be very tempting, okay, to actually say, hey, let's all work together and actually find, not all, but the authorized parties, and find the xi. You could think, for example, about a person who is very unpopular in Europe, Trump. And so what happened is that the Democrats wanted to find the tax declaration of Trump. So now you're going to secure multi-party computation with Trump, clear? Which involves his tax returns. It's going to be very, very tempting for people to say, hey, we want to find the tax returns from Trump, even though that should not be the output. It just may have something which is part of the input. Clear? Now, obviously, if you do such an illegal operation, in the first case, you probably break some law. In the second case, you probably also break a law, for sure, but you may also break the rules from the bank or the other financial institution. So therefore, what they may want to do, they may want to find the parties who did this. Okay. Now come the main concept here, is that unfortunately, if you use Shamir Secret Sharing scheme, they do not have to use their own shares. What they could do, they could use other shares. Why? Because they know all the n shares. Clear? So as I said, when you use Lagrange interpolation, you can reconstruct the whole polynomial, so you know everybody's L shares. And then to the algorithm, you will not give your own shares. You'll just pretend to be somebody else. And you will then use their shares, which you can recompute anyway. And so you frame the other participants for having done the above. Okay? So today, there is a journal which is actually called IEEE Transactions on Forensics and Security, if my memory is correct. And so this forensic aspect is important. And so therefore, I said to one of my co-authors, we need to analyze this further instead of just having this trivial comment. And so what we actually doing, I don't know whether you actually have here the goal. Okay. So, okay, I will give you the goal here. So the goal of what I'm going to explain now is to look at schemes besides Shamir's secret sharing scheme and see whether framing is possible there or not. Okay. So the first thing that I need to explain is seniority in access structure. It was introduced by Simons, so it's very old in 1988, and we had to wait until it was properly formalized by Farras and Padro in 2012. So when we have an access structure for a certain secret sharing scheme, we may then define a relation that basically says that if we have P larger than Q, that's going to happen if you have a subset X, where X is a subset of all the participants. And now, if you take a union with Q, if X union Q is in the access structure, if that implies, so you can assume that X is not in the access structure. So if you have X and you take Q and now it becomes an access structure, then it implies that X union P will also be in the access structure, and that for every non-authorized X, for authorized is trivial, for every non-authorized X, then we actually say that P is larger than Q. The participant P is larger than participant Q. Okay. So roughly speaking, that means that P is at least as powerful as Q, because everything Q can do, if you replace Q by P, P can do too in a coalition. And so my co-author, one of my co-authors for this paper has done a lot of work in game theory, and so this is called Isbell desirability relation in the game theory. So what is ideal secret sharing? I told you that Shamir secret sharing scheme is perfect. So that means that for this scheme, you basically, if you are unauthorized, you have no clue about what the secret is, giving your shares. But the second property, which is needed for ideal, is that the size of the share is the same as the size of the secret. Okay, and it was proven by Green-Karin and Hellman in the 1980s, that, or maybe in 70s, that you cannot go smaller. The size of the shares cannot be smaller than the size of the secret, if you want perfect. So a theorem that we were able to prove, and for the details, you can look at one of the references. But then if we have an access structure or an ideal secret sharing scheme, and X be an authorized coalition containing a participant B in X, which is contained in some minimal authorized subcoalition of X, then suppose that A is larger than B for some A that does not belong to X, then X can frame A. Okay, it's quite interesting because A is above, so it's kind of meaning the following: that if you're inside an organization, we'll talk more about hierarchical in a minute. If you're inside an organization and you have somebody more senior, then the people who are lower seniority can frame the people who are higher seniority. Oops, that's a problem, isn't it? Yes, that's definitely a problem. Okay. So now there's something which was introduced by Simons and then studied by others afterwards. It's called hierarchical secret sharing schemes. So let's give me two examples of hierarchical secret sharing scheme. If a significant sum of money is being transferred from a bank to another bank, and this is happening in practice, it doesn't have to be vice president, it could be two people, vice managers of a local branch, if the amount is not too big. So, but even for relatively big, small amounts, it doesn't need to be huge amounts. You have this structures that are in place. So you need approval of 2 vice presidents or 3 senior tellers, or a vice president and 2 senior tellers. Okay. So you have an or between those. You have or. Now, in the other example, we have 15 members of the UN Security Council, consisting of 5 permanent and 10 non-permanent countries. A passage of a resolution requires approval of at least 9 countries, subject to a veto by any of the 1 permanent members. Okay, so that means that you have no veto, and between those 2, you have to have an and. So in the first, we have an or, and the second one, we have an and. So you immediately see you're going to have 2 types of hierarchical access structure. The one is called disjunctive, which corresponds to an or, which you see with the symbol that exists. So here you see the symbol here, there exists, which corresponds to the or, as you know. And then here the other one is called the conjunctive, and then there you have the for all. And so what you will do, you will partition the set of participants into disjoint subsets. P0 is a strange way that some people in this area call the dealer. P0 is just the dealer. If you look in secure multi-party computation, we never consider the dealer as a party. In secure multi-party computation, you do, but in other things you don't, okay? Because in secure multi-party computation, every party will play the role of a dealer. But so P0 is the dealer. And so that's what I want to clarify. So for many people, P minus P0 are the participants. And so then you have K1, K2, Km that basically say that you're going to have cardinalities as we had in our 2 examples. And then observe that the first example, the one from the bank, can be achieved by a disjunctive hierarchical scheme, with this K being 2 and 3. And when you look back at the previous slides, then you know what the 2 and 3 is. And for the hierarchical schemes, you had 5 and 9. And you clearly see that you had this 2 there for the vice president and then 3 for the other. You could say there is a third one. Yeah, but the third one follows from the fact that you have these ors. And so therefore, the third one falls from these 2. Because the way it's organized is that if you are higher up, you can play a role of a person lower down. Okay, so now I'm going to give an example of framing. And I was planning to use the board. And what people have discovered is that hybrid lectures and hybrid teaching is the worst way of doing it. And where most of the year, many faculty members just refuse to teach hybrid because it's too difficult. Okay, so I will try to explain it using the mouse. So why did I put in these 2 matrices a line? Because the first one is actually, the first row refers to the secret. So we have H1, H2, H2, H3, H4, so 4 rows below. Those correspond to the 4 participants. So 1 row corresponds to participant 1, then the second, the third, and the 4th participant. So what's going to happen is that it's very strange, because if you look at the first line, that's not corresponding to the secret. What the secret is, in this case, the first line on the right-hand side, you have a 1 there and a 0. But suppose you would have a 1 and a 1. Then what's actually going to happen is that you will compute the shares, and the first share is S0, that's the secret. As you're going to take the first column, you're going to multiply that with T1, and then you're going to add the second column, and then you're going to multiply with T2, and the dealer is going to choose T1 and T2 randomly. Kind of. Because if you do this, what's going to happen is that you're going to get a random secret. So imagine that the first row would have 1, 1. Then it would be T1 if the first randomness you call T1 and the second one, or let's call it R1 as we cryptographers usually do, R1. And then the second one, R2. Then the secret would be nothing else than R1 plus R2, if you would have had a 1, 1 there. Now, if you only have a 1 and a 0, as in this case, then the R1 to that corresponds to secret. So it's a little bit differently than what people who work from a theoretical computer science look at this. the way that people in combinatorics are looking at these ideal secret sharing schemes. Okay, so I had to clarify that. So we're working in the integers mode node 3, that's set on the top. And now what you can look at is, except for 3 and 4, they can actually, any of these two can compute the secret. And the way you can check it is that if you work mod 3 and you look at 1 and 2, if you take the row H1 and you subtract of that the row H2, you're going to get a row 1, 0. And then with a little bit in linear algebra, that means that if you look at the share that 1 has and you subtract the share that 2 has, you're going to get the secret. So now if you look at 1 and 3, so if you multiply H1 with 2 and you subtract H3, then you're going to see that you're going to get as a row the 1, 0. And so therefore you are able, these two with just what I just did, the computation I just said, they're able to recover also H0. And so you can continue doing that. And any pair of participants, apart from P3 and P4, form an unauthorized coalition. Okay? And so we have actually two groups of equivalent participants, P1 and P2, and P3 and P4, with participants of the first group being more senior participants of the second. And so therefore we have an hierarchical scheme. And so the access structure is hierarchical and bipartite. So let's now look at this, because what we said earlier on is that people who are lower in the hierarchy, but that's not for a hierarchical scheme, that was basically with a different definition than I'm using now. So people who are lower up can frame people who are higher up. Okay. But if you look now at P1, and P1 is higher up here, then what actually happens is that P1 will always know the shares of P3 and P4. And so P1 is little P1 and P2, as you see. So if you look here, that capital P1. So combinatorics people lose for participants lowercase symbols, and for subsets uppercase. Not what we do in theoretical computer science. And so when you look at P1, that actually means that subset. Okay. And so the subset of the participant 1 and participant 2, they can recover S3 and they can also recover S4. So it looks the opposite of what we were describing before. It's not completely true, because we're looking here at not just ideal secret sharing in general, but at the hierarchical ones. But there's something also quite interesting. So I'm going to make a few reflections. If only P0, P1, P2, and P3 would participate, P0 is the dealer, forget about that. That's the way combinatorics people look at it. Then all of them would be in equal the seniority, and the scheme would be 2 out of 3. Okay. Now what happens is that P3 was weakened by the introduction of a clone. Okay. And cloning of candidates is a well-known phenomenon in voting. Okay. So if you look indeed at this matrix, and if you now look at the row on the right hand side where you have H3, there you have 1, 2. If you now multiply it with -1 over the integers mod 3, -1 mod 3 is 2, and -2 is 1 mod 3. And so you indeed see that the shared part 3 will get is nothing else than minus the shared part 4 gets. So it's kind of that they know each other's share. They get almost the same share. So now what is cloning? So Condorcet actually looked at cloning long time ago, centuries ago. And so he looked at, if you're using plurality voting, and you now have somebody that you don't like. So suppose that it doesn't work in Britain, but so suppose that you would be in an election and you would have the Tories and the Labours. And now the Labour want to win. So what are you going to do? They're not going to have one Tory candidate on the ballot. They will have two Tory candidates on the ballot. Clear? And one Labour candidate. By nominating a second Tory candidate. In Britain, it's not possible, but in some other countries, this will be possible. And so what's going to happen is you're going to divide the votes between these two Tory candidates. It's kind of what happened to the father of George Bush, Bush the First, when Perot ran in the election. So Perot was also on, he had many companies, etc., and lots of money. So he was a right-wing candidate. And Clinton was a left-wing candidate. So there were two right-wing candidates. For a while, Perot was basically winning, I mean, in the polls, but then he was being regarded as against certain. So in the United States, what you can do, if you have a mortgage, the interest on the mortgage you can deduct from your taxes. And he was going to abolish that. And so all the mortgage companies were running ads on the TV against him. Don't vote Perot, don't vote Perot, don't vote Perot. But anyway, there were people still saying this is the candidate who at least has a vision. And so the votes were split between Bush and Perot. That was a cloning. And that way implied now that the Clinton won the election. So there's another thing, is that the reason P3 and P4 can be framed is that X is not the weakest authorized coalition, as P2 can be replaced by P3, which is also weaker, and still have X prime authorized. Okay. And that turns out to be an important concept. So now we have is a new definition that says, we have an hierarchical access structure, and then X be a coalition. So if P belongs to X and X does not belong to X, with P larger than Q, that's the definition that we used earlier, then passing from X to X minus P, so you remove P, but then you put Q in place, is said to be a shift of X. Okay? And so we call unauthorized coalition X is said to be shift minimal authorized if one, any subset of X is not authorized, and two, any shift is not authorized either. Okay? So that is the definition. And then what we were able to come is a theorem for hierarchical secret sharing. We have other results, which I'm not going to explain, which I refer to 1 and 2. And so we have theorem 2 there that says that K1, Km, those are these values that we had 2 and 3 for the case of banks, and then I think it was 12 or no 5, 9 and 5 for the case of the United Nations. So those are these values. And suppose that hierarchical access structure is one of these two, either the constructive or the destructive. And then what we have for we have this part A is that in the disjunctive, any shift minimal authorized coalition of I type can frame every participant from level I and higher, not belonging to it, and cannot frame any participants from level I plus 1 till M. Okay. So you get something very similar that we had the first one, but this time we had to add shift minimal. Okay. And then we have something similar for the other hierarchical secret sharing scheme in a similar way. Okay. So those were for details. There are other results that we have also, which you can look up in the references. So now come the conclusion and the open goals. So one of the things that I was interested in, but we didn't find a lot of results on that, so therefore we didn't publish this, except with the statement that's here, is that it's easy to make examples of framing for non-ideal schemes. So in that case, a participant may receive 2 or more shares. Okay, you could call them sub-shares. So some people call them shares. To be used depending on the authorized coalition. So if you're with, let's say, your managers, then you're going to use one of your 2 shares. But if you're not working with your manager and with all the tellers together, or a large fraction of tellers, then you're going to use the other share. Clear? And this makes the issue of framing much more complex in the sense that such a participant might be partially framed for one of the two shares, but not the other. And so this is the comment that I just added to this week to my slides, is that except for rational secret sharing and its variants, the cryptographic community lacks to consider game theory and social sciences. And so one question in general, in what context can one frame? Okay. There has been a little bit work on traitor tracing, but it's not massive amount of work that you see where people looking at social sciences in cryptography and then making things from that perspective, looking at that from that perspective. So now I'm going to go to the references. So I'm going to start with the third reference. So the third reference is realistic versus rational secret sharing. And that was presented by my co-author at GameSec 2019. And so GameSec is a conference that is basically about the intersection of game theory and security. And now I'm going to go to the first reference. And that's basically appeared in the IEEE Transactions on Information Forensics and Security. And why is there now a second reference? Okay. So it's a very interesting. So when you look at the IEEE Transaction on Information Forensics and Security, then what you find out is that most of the papers are on forensics. And so therefore, we assumed that in order to submit a paper, we wanted to make it more easy to read for non-mathematicians. Okay. And so therefore, what I told my co-authors, Mo and Slinko, is that we should make sure that this paper is accessible as much as possible. So we made readable proofs. Then we submitted it. We had 3 reviews. I've never had a paper in many, many years that had such incredibly qualified reviews. And they said, you know, this proves it takes so many pages. If you actually know matroids, then these proofs become much shorter. And we had not just one reviewer, we had 2 reviewers who were basically both knew about matroids and know in there, one of them, we presume, in their PhD, I presume, because we don't know who the reviewers are, but we presume that that person, if we guess correctly, in her PhD actually was using matroids in secret sharing. And so we had not just 1, but 2 experts on the use of matroids in ideal secret sharing. And so our paper was accepted on the condition that we remove all the readable proofs and make unreadable proofs there instead. So reference 1 is the one that contains all the unreadable proofs, except they are readable for people who know about matroids. And I promised my co-authors that on the archive, that I actually would put the paper, the original paper, with the readable proofs on, so it would become more accessible. We had hoped it would be in the actual journal, but for the crazy reasons I just explained, it didn't happen. And so in order for people to read this who are not familiar with matroids, my goal is in the next few days to actually put it there with a statement why we put this there, despite the fact that it appeared already in a journal in order for making the paper more accessible. So that's the difference between 1 and 2. And so I would, if you want to read more and you're not familiar with matroids, I would wait until you see 2, which has much easier to read proofs. Any questions?
Please feel free to unmute and ask your questions if you have any questions.
Maybe you need to click unclick things because you did a few clicks that people could not send you chats, etc. Remember, you got some chats.
So we can stop sharing the screen.
Okay.
And just have you. Yes, please go ahead if you have any questions.
Hi, thank you for your talk. I was just wondering if you discuss any like mitigations against these framing attacks, or if you have any ideas on, or if it's sort of like inherent in how it's sort of designed.
What actually happens, which so I've done some consultancy for banks, and also there are some stories. The story that I'm going to tell has never been confirmed to me, okay? So don't quote me and say, hey, we got a confirmation. But what actually happens is that when banks get hacked or they have an internal problem, they prefer not to bring it open in the open literature, okay? And that used to be, when I was a PhD student, that used to be the case. And then I think 25 years ago or so, Citibank was hacked. They were hacked from St. Petersburg. And they actually thought it was a good idea to reveal that they were hacked and they wanted the money back, etc. You know what happened when they actually made this public, that they were hacked? I think they revealed on Friday. What happened on Monday?
The stock market dropped.
Yeah, the stock market dropped. Their stock dropped. So the clear example is when you have such a problem, you keep it inside. Okay.
But I have read, can I say something?
Yes.
But I have read, because I was doing some research in this area, and they said if you reveal that, if you patch the problem and reveal that, it might be the case that your stock increases because the problems are inevitable, but how do you deal with them quickly is important. I don't know if it's
okay.
It's
so it's kind of
argument.
what you need to do is kind of, if you are in the banking world and you want then to come out with that in public, etc., you need to have worked this out very well, talk to psychologists, etc., because psychology plays an important role in the stock market. It's not a rational, it's actually an irrational behavior, but it does. And then see what all these things are. And so then if you look at these litigations, it's not that there are a lot of litigations. Also, you should not forget that although we have 70,000 papers that just cite Shamir Secret Sharing, in practice, it's almost never used. Okay. And so it's basically academics behind their desk that making all these papers on secret sharing. You could evidently say, if you look at what I had there.
I'm not sure.
Oh, you're not sharing. Okay. But I mentioned IBM Cloud. No need to share. So if I mentioned IBM Cloud, multi-cloud, that's actually an example where it is going to be the case. But that might be from not having really deep parties. So if you look at IBM Cloud, it might be you or me who don't trust the Amazon cloud and don't trust Microsoft's cloud, etc., and say, hey, I want to use two clouds. So that then the people inside Microsoft or inside Amazon, they cannot get my data. You need two people from two organizations. So there, it's actually the owner of the data who shares the data, and then these clouds. And so in such a case, how will I know whether whether Microsoft and Amazon collaborated when they were not allowed to do that to recover my secret, which they can. And so how will I start a litigation? Okay. But the problem is that with the schemes that we usually use today, this litigation makes no sense, because you can say, hey, I was framed. Clear?
Yeah, thanks.
Any other questions? Okay, I have one question.
Yes.
So thanks again for your talk.
Thanks for inviting me.
So in the beginning, you mentioned about the participants some of them may not participate in the reconstructing the secret, right? And so the secret may never get reconstructed.
Yes, so in terrestrial crypto, for example, you don't want anybody to ever recover the secret. You want people to use it to co-sign a message or to go decrypt the ciphertext. You don't want to have parties collaborate to recover the secret. So also in secure multi-party computation, every party is going to share that xi. You don't want that to be recovered. What you want to be, when you do the full computation with all the shares, computing with shares, at the end, you're going to get shares of the final result. Those shares should be used to compute the final result. But you don't, but you have shares of everybody's input. So often you do not want that certain secrets are recovered. Okay?
Thanks.
Thanks you for attending.
So there's one. Okay, thank you. David Pim says thank you. Is there any other questions? If not, then I thank everyone and especially Ivo for the talk. Very interesting talk, and thank you for attending the talk. See you.
Thank you.
Thank you. Bye.